Okay, well, I think we can get started here. Thank you very much for joining today. I will be talking for about an hour, a little more maybe, see how things go. This is a very simple orientation session for our workshop that's coming up in August. And the goal here is to help people get started and to try to get over obstacles and difficulties so that when we start the workshop, it's formally in August, everything runs smoothly. And it's an opportunity just to go over the logistics and the organization and a little bit about CompuCell. And then we will hope that people will be ready to have everything work easily when we get going. I need to remind you that this is like all of our materials. This is live streamed and recorded. It's live streamed on YouTube and it's recorded and will be made available on YouTube afterwards. Please take the time now to make sure that if you're going to use nanoHub, you have a nanoHub account. If you're going to be using CompuCell on your desktop, download and install CompuCell to your desktop. The desktop people may find they have to wait a little bit today because there's some extra things we have to deal with nanoHub today that may slow us down a little bit. So I'll just talk a little bit about the logistics of the course, a little bit about background material. We'll talk about the hackathon, which is a lot of fun if people want to do it, where to find support, and then we'll outline how CompuCell works, and we'll run a quick demonstration of how to build a model with CompuCell and experience it. We have about 150 people registered for the course so far. That's a lot. Today we don't have a big group, but during the main workshop, we ask for your patience because we have a good team, but not a huge team. And so we'll do our best to support everybody. If anybody happens to be an experienced CompuCell user and would like to help out as a teaching assistant, we'd love to have that and let us know. So welcome to everyone. As a background of the things that we will work on in CompuCell are tissue organization. And we are interested in how cells come together to build tissues in development, how they maintain tissues during normal adult life, what happens when those maintenance methods fail in what are called developmental diseases, the most famous developmental disease being cancer, but there are many others. What happens when you have viral or bacterial infections and how the immune system responds to those infections, clearing the infection but damaging the tissue and how the tissue recovers. Toxicology, how chemical insults can cause damage to tissues and how recovery happens. How you can use these kind of computation to design optimal interventions or do drug discovery, and potentially how to use these kinds of models to do bioengineering, to design new things. In all of these cases, we're talking about situations in which we have a complex interplay of physical and biochemical processes, so that you can't understand what's going on just by looking at molecular signatures, just by looking at omics, and you can't understand what's going on just looking at biomechanics. You need both. The kinds of modeling we'll do are often called virtual tissues. These start at the level of the cell as an operative agent, an active agent. We think about the molecular control inside of cells. We think about what cells do. We think about the biochemical and mechanical environments of cells and how those three factors combine to lead to complex pattern formation. The example on the right is showing the Semitic clock oscillators that operate in the embryo during early development. They interact with extracellular fields that lead to cell differentiation. That cell differentiation in turn leads to changes in cell properties that finally lead to reorganization of the tissue to form the somites that are going to organize the segmental structure in vertebrates. This is a process that you cannot understand looking only at molecular concentrations. You can't understand it only at a mechanical level. You have to understand the integration of these signals. We have a couple of slides just showing a few examples of simulations developed with CompuCell. On the top right is an old but quite elegant simulation of blood vessels in a tissue. You have an initially non-vascular tumor which grows. As the tumor grows, it begins to send out vascular endothelial growth factor signals that lead to proliferation of the vasculature, neovascularization. And that then supplies additional oxygen and nutrient to the tumor, which then grows more rapidly. On the top left, we have another proliferative disease. This is a rare disease called polycystic kidney disease. It's currently untreatable except with a kidney transplant. In this disease, the cells in the kidney proliferate when they shouldn't. They form cysts. Patients die with kidneys the size of watermelons. At the moment, this is essentially an untreatable disease. This was work trying to understand the mechanisms of the disease to do drug discovery. And indeed, there are drug candidates now in evaluation based on this work. On the bottom left, we have a study trying to optimize laser ablation photocoagulation therapy, which is a treatment that is developed for treating diabetic retinopathy. The problem with that treatment is it damages the retina, and it also isn't always effective. And so this was a study trying to determine whether one could develop treatment strategies using existing technology, but more intelligently, to reduce the amount of damage in the retina and to increase the treatment efficiency. Finally, on the lower right, we have a simulation of a different kind of retinal dysfunction. This is called age-related macular degeneration, inducing choroidal neovascularization. In this case, the blood vessels are invading the retina where they shouldn't and causing structural loss of integrity in the retina. Diabetic retinopathy and retinal neovascularization together are responsible for the vast majority of adult blindness in the developed world in adults. In both cases, these are suggesting new approaches to treating those diseases. I mentioned toxicology. Don't know if we have any toxicologists in the audience this year, but the U.S. Environmental Protection Agency has done quite a bit of work using CompuCell to try to understand how chemicals in the environment can lead to disruption of embryonic development. The first was a paper looking at blood vessel development and interactions that could impair blood vessel development in embryos. The second one was looking at hormones in the environment and estrogen mimics, which are thought to potentially lead to urogenital defects in both animals and humans. The third one was looking at the incidence of cleft palate. In this case, the bones at the top of the mouth fail to fuse properly during development, and that can also be induced by environmental toxicants. So these are some very broad spectrum examples of the kinds of things you can do with CompuCell. Some of these projects will be presented in the breakout sessions in the second week of the course. Back in 2020, the students were interested in modeling viral infection and immune response. This was a paper that originally started out as a student project. In this, we have a simulation of a patch of lung tissue. You have a single infected cell. That infected cell produces virus, which spreads in the environment, infecting other cells. The cells send out immune signals, cytokines, that call in immune cell responses, which kill the infected cells. And we can look at the competition between the spread of the virus and the ability of the immune cells to control it. and also the pattern of damage in the tissue induced by the immune cells. We hope that that gives you just a flavor of some of the things that have been done with CompuCell. There are many, many more beyond that. But maybe some of those will pique your interest or be relevant to your particular areas of expertise. We hope by the end of the course, you'll be able to look at a biological problem and begin to frame quantitative questions that you could answer with computational models. Because simulations are useful in many ways, but they can't answer every question. And so it's important to learn how to define the questions that can be answered appropriately. Once you've done that problem definition, you have to look at the biology, which is infinitely complicated, try to determine what the most important components are and how they work, and focus on how to describe those components and those interactions. Then we have to implement those things in CompuCell3D, and we learn how to use the tools that we have, CompuCell3D Player and Wizard, to build simulations, run them, and analyze them to produce biologically meaningful results. I'll talk just a little bit about course logistics. We'll send out the links for the workshop proper and the hackathon in the next week or two. We have a set of documents. There's going to be a hackathon organization document and a hackathon Slack channel. These will be ways of people communicating to organize hackathon teams. In the Zoom, feel free to use your buttons, go slower, go faster. I'll often ask people for a show of hands about whether things are working or not. We'll also use polls. The polls will ask questions like, have you completed the exercise? It winds up that the polls, once you've answered the question, you can't change your answer. And so I'll give you a little bit more instruction how to fill those out in a little bit. All of the slides, videos, exercises will be made available. So if you get behind in some point, you'll have the ability to look at all the material after the class is over and try to catch up. As I mentioned, all the sessions are live streamed on YouTube and also archived and recorded there. We have a great team this year. Not everybody is here this evening, but they're going to be helping us out. I'm James Glazier from Indiana University. Gilberto Tomas from Brazil will be helping instruct. He's been part of this project for many, many years. Pedro Del Castel is a student who will be one of the instructors. He gave wonderful lectures last year, and he's very, very good at helping out with CompuCell. Giulio Belmonte is professor at North Carolina State University. He'll be helping instruct. Jim Sluka, senior scientist here at IUB, will be available especially for the hackathon. Joshua Pontes Serrano from NIH will be helping teach a few modules. So will Priyam Adyapak from Duke University, TJ Sigo from University of Florida, and our course coordinator is Dr. Hayden Fennell this year from IUB. And we thank everybody for their volunteer services. Nobody gets paid for doing this. It's all volunteer. And we really appreciate everyone's effort. In the past years, we've tried to do everything in 1 week with 4 modules per day. That's pretty intense. Means that it's hard to catch up if you get behind. This year, we're spreading the course out over a little bit more time in terms of the number of days, and we're trying to make things a little bit less intense. So we will have it every day, opportunity for quick questions before we start. At 10 a.m. in US Eastern Time, we will have the first module. Each module will be 90 minutes. We'll try to make it about half lecture and about half exercises, although some modules may be more exercise, some may be more lecture, depending on when they come in the course. In the end of each day, we'll have a module which will be more extensive exercises, a bit of a lab with assistance. And the goal of that is to find trouble, troubleshoot, consolidate your understanding, and ability to explore a bit in more detail than we can do during the 90-minute modules. And after that, we have an opportunity to ask questions and have discussion. Although in my experience, by the time we get to that point, people are pretty tired. So there's not a lot of questions usually at the last. The first week will start with a day of Python tutorial. If you don't know Python or you don't know Python very well, we strongly recommend it. It's going to be focused on things you need to know to write Python code for CompuCell. Then we'll have 4 days of basic CompuCell, how to make cells, how to make them stick to each other, how to make them move, how to create chemical fields, have cells absorb and secrete chemicals and respond to chemicals in their environment. The second week will deal with more advanced topics. We'll talk about modeling biochemical networks, how to integrate networks with CompuCell cells, how to make cells that are structured spatially for modeling cell movement or epithelial organization, how to use links to make mechanical structures and rigid structures. We're going to introduce additional advanced topics. We still have to decide on the details for that Wednesday. Then we'll have deep dives into a couple of the most interesting sophisticated models. We'll have several speakers who've published important models, explain how they work, have you run some of them, and explain the code and how to think about those problems. We'll also talk about things like how to extend CompuCell if you want to, because it's designed to be extensible, how to do parameter scans and high-performance computing applications with CompuCell. Throughout that period, we'll be building up to the hackathon, and we'll have the model building hackathon in the final week. We hope that people come in. It's not required to do preparation. We cover everything in the class, but in our experience, people find it a little bit easier and more productive if you do a little bit of advanced preparation. And I'll talk a little bit about what you might want to think about in terms of preparation beforehand. Again, we try to cover everything in the class, but it goes by pretty fast. And so a little bit of background is helpful for people. We will try our best to be available to answer questions and help with technical issues throughout the workshop. I want to talk a little bit about background knowledge and reading. Don't worry if you don't know all these things. Nobody comes to this knowing everything, unless they've happened to be doing this modeling for a long time themselves, in which case they probably should be helping teach the class rather than taking it. And you'll certainly hear me say very often that there are things that I don't know. I've been doing this kind of work for 30 years, and there's still a lot I don't know about it. And so we're all learning together. And one of the things that's great about this class is it's very diverse. Over the years, we've had high school students take the class. We've had PhD students, postdocs, professors take the class, retired professors take the class. We've had people who were pure mathematicians, biologists, bioengineers, surgeons take the class, toxicologists. And so the diversity is a great strength. And one of the things that we can do is use the Slack and the breakout rooms to team people together so that if you're a biologist, an experimental biologist who hasn't done any mathematics, and there's a mathematician who hasn't done any biology, perhaps you can work together and help each other learn. So that really is a great strength. Geographical diversity and age diversity, background diversity are great strength in this class. There are 5 core areas that we will need to work with building these kinds of models. 4 of these will be terms that are probably familiar to you. The very first one may not be so familiar, principles of modeling. Sometimes that's called quantitative thinking or computational thinking. But it's really about how you organize your approach to using and building models. Nobody needs to need all of these in depth. Depending on the particular problem you're working on, you may need to know more about some aspects than others. but we'll all need to know a little bit about all of them. Of course, we come into these things knowing something about everything of this, but we may have to deepen our understanding in a few areas, and different people will need to work perhaps in different areas. Principles of modeling is the one that's probably taught the least formally in schools. This is trying to define the questions you can answer with models, how to select, how to measure the systems you're going to quantify, how to conceptualize and construct models, which is not an easy task, how to decide what components and mechanisms are important biologically, how to represent those computationally. Biology uses the concept of networks very freely. How do you map that? How do you build network diagrams? What are the limits of the models you write? How accurate are they? What circumstances do they work on? How do I determine the parameter values of the model? How do I know when I have a model that works or doesn't work? How do I use models to explore scientific uncertainty, or to design new experiments, or to interpret experimental data? Python, we will need a little bit of programming, not a lot, but a little bit. You need to know what basic Python syntax is, how loops work. The one thing that is probably least familiar on this list, if you're not a Python programmer, is the concept of a Python list or a dictionary. Python has rather interesting object classes. In particular, Python has a concept of a dictionary where you look an object up by its name. And that's a very powerful concept, and CompuCell uses that repeatedly in the way you interface with it. You'll have to know a little bit about what are called Python classes and scoping, because that'll determine a little bit about what information is available where, and how you reference information. We'll cover all of that in the class, but if you've never used Python before, it can be a lot to learn at one time. And so we do encourage you to review just the basics of Python. We're sending out a Python cheat sheet that has the simple syntax for Python. There are many online courses that are free that you could look at. Again, you don't need very advanced Python. You just need a few things, but it will be helpful if you have a chance to do a little bit of prep if you haven't used Python before. Maybe it's worth asking while we're here, what fraction of people have used Python in the past? Maybe it's just, we can just ask you to raise your hand if you've used Python in the past. So a few people have, about half of the people have, half haven't. That's fine. Again, we will cover everything you need. But if you haven't used Python before, you definitely want to take the Python Bootcamp day at the beginning of the course, but you might want to do a little bit of review beforehand. The amount of biology you need is not enormous either. Clearly, since we're going to be talking about biology, it's useful to be interested in biology. These days, a lot of biology is omics and molecular information. That's helpful, but it's not the core of what we do. The core of what we do is in cellular and developmental biology, tissue biology. And so the fundamental question we're going to ask is, what are cells and what do they do? How do cells produce forces? How do cells move? How are tissues built? Tissues consist of cells, and they also consist of extracellular material. How does that extracellular material created? How is it moved? What does it do? There are two fundamental biological organizations, mesenchyme, which is three-dimensional tissue, and epithelia, which is sheet-like tissue. You want to understand the differences between those and how they work. Cells are oriented. They have what are called polarity. And they also have a second polarization axis called planar polarity. Those are quite important basic concepts. We're going to have the concept of networks inside and outside of cells, in particular signaling networks, how cells interact with the outside world, metabolic networks, how they synthesize and break down chemical compounds, and regulatory networks, how they change their genomic state. What chemical reactions are? What are regulatory interactions? How do networks control cell behaviors? That's actually still not very well characterized scientifically. What are the basic motifs, patterns? Because you see the same patterns in biology over and over again. And then some higher level things. Blood vessels are very important in the body. How do blood vessels work? What do they do? And often people are interested in cancer, and cancer has its own set of questions and properties of cells and tissues. And at last, we need to know, if we're not biologists to begin with, how biologists represent information. Biologists think about biology very much in terms of diagrams. We have to learn a little bit about how to interpret a biologist's diagrams. We're going to need very little physics. We try to minimize the amount of physics we need, but it's helpful if you know a little bit. The ideal gas law, how gases expand and contract, very simple, typically learned in high school, is important. How springs work is important. Why do we need that? Because CompuCell is based on a concept of constraints, and a spring is a classic constraint. And so if you understand how a spring stretches and retracts, you understand the basic mathematics and physics of CompuCell. We need to understand how diffusion works. Diffusion is the main way that chemicals are distributed in the environment if there isn't flow. In the blood, there's a lot of flow, but in tissues, there's much less fluid flow. And so the main transport mechanism is diffusion. We'll discover that there are concepts of diffusion length and diffusion time, how far chemicals get and how long it takes for them to get from one place to another, are very important in biology. We're going to understand how cells move. If we apply a force to a cell, how fast does the cell move? It's a force-velocity relation. If we push on a tissue and it changes shape, how does the shape change depend on the force? That is a constitutive relation. It's useful, although not essential, to understand the so-called statistical mechanics, the mathematics behind the core algorithms inside of CompuCell, something called the cellular POTS or GGH model. Those are things that will help you debug simulations that aren't working properly, but they're not absolutely essential to know. And it's always helpful to understand a little bit about fluctuations in biophysics, but not essential. Similarly, we'll try to minimize the amount of mathematics people have to know. The idea of first-order differential equations, rate equations, which govern chemical reactions and signaling networks and metabolic networks, and gene regulatory networks, those are very helpful. Those can be described by the concept of dynamical systems. Again, if you don't know it, you don't need to know it. But if you do, it will help clarify how some of these things work. These are stochastic systems also. And so knowing a little bit about probability, statistics, and fluctuations is helpful, not essential. How you represent chemical reactions mathematically, we'll go over in the class. Herbert Sauro teaches a great online class every year, a few weeks before ours. Strongly encourage you to take it, if not this year, another time. And two key concepts, which are stability. If I have a system and I perturb the system, does it come back where it started or not? It's the question of stability. And the second one is sensitivity analysis. If I change parameters because I have different values, I'm older, I'm heavier, I'm younger, how does the result of my system change? That's called sensitivity analysis. There are quite a few materials available. You certainly don't need to read all of these or any of them in full detail. and different people will have different opinions about what's useful. There's a nice paper called 10 Simple Rules for Your Mathematical Model that we'll share with you. It's written by some Canadian students. It's really about different modeling methods from the ones we're going to focus on, but it's still very useful. We'll also have a little draft paper, which we've written on the topic, which we'll share with you as well. For Python, I particularly like the Rosalind package for learning Python. It's a free open source online package, but there are many, many ways you can learn Python. And I think that you shouldn't have trouble finding that material for free if you look for it. Network modeling will be using the Tellurium software package. That's free, open source. It has excellent tutorials and documentation online. If you want to learn a bit of mathematical biology, I really like the book, Essential Mathematical Biology by Britton, which is available, but Wikipedia has very good material as well. For the basic biology, Gilbert's Developmental Biology is wonderful. The current edition is very thick and very expensive, but really what you need are the basics. And so you can go online and find a 25-year-old copy of Gilbert for $2, pick it up, and it'll have almost everything you need. It's a lot easier to read than the current edition. For physics, Phil Nelson's Physical Models of Living Systems is wonderful, introduction course. The Physical Biology of the Cell is a beautiful advanced course, but it's pretty sophisticated. But it's a wonderful reference text if you have it. We have a paper which I'll reference again that explains the guts of the CompuCell methodologies. And if people have any suggestions for good sources, resources, reviews for these concepts or others, if you send them to us, we'll definitely put them on the list and make them available to everybody in the course. You can find most of this material on the CompuCell website. There are online manuals for Python scripting and basic Python. There's a somewhat out-of-dated quick start guide that would walk you through the basics of what we'll cover today. It was written for an earlier version of Python, but everything in it still works. Somebody wanted to help us rewrite it to be more modern, that would be great. There'll be a Slack channel for the class, Google Drive for the class. We'll also distribute everything on the CompuCell website. Tellurium manuals again, Tellurium Read the Docs is great. Quick reference guides. There are going to be a couple of cheat sheets which were sent around. 3 cheat sheets, one on Tellurium, one on CompuCell, and one on Python. I strongly recommend that you print those out. I have them on your desk. The Slack channel is a good place to meet people, ask questions, get help. Encourage you to use it. If anybody has trouble getting into the Slack, please let us know and we'll do our best to help you out. The quick references, again, there'll be a Python cheat sheet, about 5 pages. You don't need all of that material, but the basics are there. CompuCell quick reference guide explaining the syntax and how CompuCell works. That Tellurium quick reference guide as well, just 2 pages. I mentioned this article by Canadian grad students on modeling. It's a wonderful place to start to understand mathematical modeling of biology. And our paper, Magnetization to Morphogenesis, which talks about how CompuCell works inside. We're going to have a hackathon. I hope that many of you will participate in the hackathon. I'm going to do a quick poll, just asking you what you think you might do in terms of the hackathon. Please let us know. If you say you want to participate in the hackathon and change your mind, there's no obligation. If you say you don't want to participate in the hackathon and decide you want to do it, there's no obligation. But getting a little bit of information about how many people might or might not participate now will help us do some planning. So I will ask everybody in the room to respond to this survey. It'll also be a way of getting used to using surveys in the context of Zoom sessions. So would everybody please take a quick look? Let us know what you're thinking about the hackathon. But at the moment, I have a 0 participation rate, so I'm not going to go forward until everyone's answered the question. Again, there's no obligation to stick to what you say here, but it will be very helpful to us for planning if you do answer. I should say about the hackathon that you don't have to have a project in mind to participate in the hackathon, and you don't have to be experienced to participate in the hackathon. Teams are always looking for members, and they're always looking for members with diverse backgrounds. So if you're a biologist who's never done any modeling, you can help read the papers and define the model. If you're a computer specialist who's never done any biology, people will need your help. If you're a mathematician, people will need your help. Even if you've never done any of those things, people need help organizing and thinking about problems. So you shouldn't be shy. Building teams is a lot of work. It's very rewarding, and it's something that people can really complement each other doing. One of the things that I really appreciated in past years with the virtual format is we'll have a team that consists of one person in Australia, one person in India, one person in the Netherlands, and one person in the US working together. And it's wonderful to see people build these international teams and work together. A few years ago, there was a team that started a company after the hackathon based on what they did. So a lot of people have started PhD projects in the hackathon. A lot of people have started scientific papers that were published in major journals in the hackathon. You're not going to finish a major project in 2 days, but you can get surprisingly far if you focus on it and work in a team. The hackathon structure will be 2 days of intense work, Saturday and Sunday. We'll have 2 opportunities, not required, but optional, for people to present their ideas in short talks and try to recruit teammates. We'll have documents where you're going to put in your ideas and develop your teams together. We will review suggested ideas, not because we want to veto things, but because sometimes people have wonderful ideas that aren't a good match for CompuCell. And so we want to try to minimize the level of frustration people have by saying, gee, this is a great idea, but it's too ambitious. Maybe we can simplify it. Or this is a wonderful idea, but it's not a good match to what CompuCell does. If you want to participate in the hackathon format, but don't know what you want to do, a great way to do that is to take a paper that was published in this area using a different modeling framework and reproduce the results of that paper in CompuCell. That's pretty manageable, and you learn a lot doing it. Something I still do myself when I want to learn. And so if you want some suggestions about possible papers in your area of interest that could be reproduced in CompuCell, please ask us and we'll do our best to help. During the hackathon, we'll have a morning check-in and a noon check-in. At the end of each day, we'll ask each team to do a brief report on what they've done. At the end of the whole thing, we'll ask people to do a slightly longer report on their projects. And we'll do our best to provide post-hackathon support to people so that if you have a great idea and you want to keep developing it, we'll work with you, help you make that happen.
James, someone asked you to repeat what you said previously, I think, if I'm not mistaken, about help with reproducing papers.
Okay. So if you are interested in the hackathon, but don't have an idea of what you personally want to do, and you don't find a team that you want to join, one way to do the hackathon is to take a published piece of research and reproduce it. There are other modeling frameworks that do similar things, for example, PhysiCell or Morpheus. You could take a study that was published using PhysiCell and build a version of that study inside of CompuCell. You'll learn a lot when you do that, and it can be very, very helpful for understanding. And it's a little bit less work than starting from zero and building a model of a new system. And so we can help you find possible projects which you could do in that way if you're interested. And there's a list of those. We can help you find more if that's helpful. Okay. The only thing we really ask of hackathon participants is that you think carefully about what you want to model and why CompuCell is the kind of framework to do that modeling. And if you can identify those things beforehand, that's very helpful. You need to have a description of yourself and your skills and your goals. It's fine to be a beginner. And if you're going to be a team leader, you should have an idea of what you're looking for in teammates, how many people you want to work with you, what their skills should be, and so on, so that you can assemble a team that's productive. We'll do our best to support you throughout. If you're going to be in a hackathon, you'll need a little bit of Python as it's sort of a sanity check. If you can do the first 5 sets of exercises in Rosalind, you certainly know enough Python to be able to make this work. As far as team size goes, in our experience, teams of 3 to 6 people work about the best. We've had people work on their own or in twos. We've had people work in large teams. It can be fine in any of those situations, but fewer than 3 becomes a lot of work for each individual. More than 6, it can be unwieldy to manage. So ideal team size is probably about 3 or 4 people. I'd like to move on now and talk about the CC3D. This is mainly a troubleshooting exercise for today. CompuCell comes in a desktop version and a nanoHub version. And unfortunately, right at the moment, there was an update, and the online version of CompuCell and nanoHub, the main one, has a little bit of a problem, which we're getting fixed. nanoHub is not our package, it's not our framework. nanoHub is a NSF-sponsored public server, and we don't manage it. And so updates have to be done on request, and so they may take a few days to happen. We have a workaround for today. It's a little bit clunky, and so people using nanoHub may have to take a little bit more time than usual to use it. I ask for patience from the people who are using the desktop while we help the nanoHub people. Maybe before we get too far along, it would be worth doing another poll. And let me just ask you where people are in terms of getting CompuCell going. And so I'm going to ask you just 2 questions. The first question is, what kind of CompuCell are you going to run? Are you going to run on nanoHub? You're going to run on Windows locally, Mac OS locally, or Linux locally? And the second question is, if you have made that decision, you could say yes to more than one. Do you have it working or not? So we know how many people will need to help. And again, I'd like everybody, this one I need everyone to answer. So we have, I think, about 10 or 11 people here today. I need 10 or 11 people to answer. So we have one person who's having trouble with nanoHub, several people having trouble with desktop. Please text Pedro and ask for help through the chat. We can probably help you with nanoHub issues today. Desktop install we may have to do offline in the next few days. There's still some people who haven't answered the poll, so please, I need everyone to answer that poll. it looks like the majority of people here today are planning on using nanoHub. As I say, normally nanoHub works very well, but right at the moment, the main deployment of CompuCell has a problem. And so just for today, we're going to have a slightly awkward workaround for that, which we'll have fixed by the time we have the course. Again, if you're having trouble, either with nanoHub or with CompuCell Desktop, please reach out to Pedro for help. So once you have CompuCell running, there is an editor called Twidit++ and Player, which is a tool for running, visualizing, and modifying as they run simulations. Twidit++ has a specific feature which is very useful. It has prepackaged. Yes, if you are running CC3D on a Mac M1, you will either have to download the newest version, which is not yet fully released, or you will have to run on nanoHub. Apple made a mess with the M1, and so support on the M1 is not so simple. If we can get it working for you, we will, but we can't promise on that. Sharon asks, which is the latest release? I think we have 4.4.2 in beta test.
The betas you have to get through our GitHub. I'll go get the link for people who know how to use GitHub.
This is our attempt to get the M1, M2 problem for Macs fixed. They didn't make life easy. Apple never makes life easy. But the nanoHub normal, that's one of the reasons we use nanoHub, because that way there's no issue of installing locally. And normally nanoHub works great. It's just that right at the moment they made a mistake. And so we're dealing with that. Okay, good question. Okay, the key thing we'll see with Twidit, let me come back to that for a second, is that it has what are called code snippets. Everything that you would typically want to do in CompuCell in a program is there as a code template. You may need to do some editing, but the editor knows if I want to do something to all cells of a given type, what do I write? So you don't have to memorize things. It helps a lot because you don't have to look things up. People seem not to use that much when they're actually writing code. I don't understand it. I use it all the time. Another thing which is a bit new, which I'm still exploring, is that ChatGPT knows CompuCell code pretty well. And so very often, if you go into ChatGPT and say, give me CompuCell code to do something, it will give you pretty good code. Typically, you have to do a little bit of editing. Sometimes it'll fail. But I'd encourage people to try out ChatGPT for model definition and also for building computational models. I think we'll learn. I think as time goes on, it will be able to do a lot. So it's worth exploring that. Okay, so installing and running CompuCell. Most people seem to have it going. Again, on the desktop installs, I don't know whether we'll be able to get that all working for you today. Let me make sure that the breakout rooms are turned on. They may not be turned on. Let me turn them on. Hold on a second. I'm going to create a breakout room so if people need help that you can't do in the group, we've got that available for you. And again, you don't have to use these at all, but they're available if people need them. So we'll do our best to get everybody on that. We guarantee everybody will either be able to use nanoHub or desktop. What we can't promise is that if you have a difficult computer at home, that we can definitely get CompuCell running. Sometimes people have strange varieties of Linux, for example, that are not easy to deal with. We can't always help with it. Okay, if you do want to install CompuCell on your desktop machine, you can go to the CompuCell website. There is a downloads page that will take you to SourceForge, where you can download the appropriate versions for your code for your computer. If you're on Windows and you're used to Microsoft installers, the current Condo release is a little bit more complicated. And so there are detailed instructions, but if there is an issue, please reach out to us for help walking you through that installation. Again, SourceForge has the downloads that you need. You may very well need to run, you almost certainly will need to run the installer as an administrator. And you will almost certainly have to override the security warnings that you get when you try to do the installation. Both Windows and Macs have gotten more and more paranoid about installing third-party software. And so you will have to go in and tell it that our software is all right. If you don't know how to do that, you can look it up online, or you can ask Pedro or Giuliano for help. If you're using a desktop and you have it running now, I'd ask you to launch Twidit++. I'm now going to take a few minutes, and then you can explore the built-in demos while I explain to the nanoHub people how to use CompuCell online. And as I mentioned, the nanoHub is a little bit difficult right at the moment, and so I ask for your patience today while we get these things ironed out. Okay, CompuCell webpage has nanoHub information. Normally, we would be using CC3D base 4X, which is the standard deployment for CompuCell on nanoHub. Unfortunately, that is broken at the moment. And so we will be doing a workaround. There is a specific tool using CompuCell called Slime Mold. It's not perfect, but will allow us to do what we need to do for today. And there'll be a few inconveniences using that. And I do appreciate your patience as we walk through that. Okay. So the first thing that I'm going to ask you to do, if you're a nanoHub person, is I would ask you to go to nanoHub and log in. So everyone in the world can have a nanoHub account. It's open to everyone. And so please, everyone who's not using the desktop version, go to nanohub.org and log in. If anybody has not set up an account, now is the time to set up the account. When you do that sign up, you have an option. If you're in the United States, you would sign up with an affiliated institution. If you are not in the US, you can sign in with nanohub.org account or with Google. And I'll give people a few minutes to do that so that we can make sure that everybody's on board before we go forward. Maybe the best thing to do would be just with the emotion responses in the Zoom. If you could please indicate whether you have nanoHub running or your desktop. So give me a thumbs up signal when you've got something running, whether it's nanoHub or desktop, and I'll know whether to go forward. Again, if people are having problems, please text Pedro in the chat. Sharon, you're on nanoHub. That's good. Okay, great. Don't be shy about asking for help. Does anybody need help at the moment? No. Okay. Once you've gotten into nanoHub, you will need to learn how to migrate to manipulate nanoHub. nanoHub has a concept of a dashboard. To get to the dashboard, we can click at the top left, the nanoHub icon. Under menu, there'll be an option to select the dashboard. And that will take you to a control screen where you can search nanoHub applications, launch and end jobs, manipulate your storage. I actually have CompuCell running at the moment. I'll terminate that for the moment since we're going to restart it together. For today, you're going to search for the slime mold tool. Go to all tools. In the search bar, type slime. There's only one nanoHub tool called slime. It's CompuCell3D, CC3D slime mold simulation. Hit the heart to bookmark it so you have it available to you afterwards. Everybody got that? And then launch it by hitting this icon next to it. It'll give you a warning, which you can ignore, and then it will open CompuCell. So I want to wait. How many nanoHub people do we have on now? I see one check, two checks. Are you able to get to this screen? Is anybody having trouble getting to the screen? If you need help, speak up. Okay, there are a couple of things that I need to tell you. The first thing is that in nanoHub, sometimes there are issues with redrawing the screen. When that happens, select the bottom right-hand corner of the bounding box of this application and move it, and that will force it to redraw. You can resize your windows inside that bounding box by pulling on the corners or using the maximize and minimize buttons. The actual computer simulation is hiding here in this gray area. To see it, there's a very powerful command that works in Windows, Linux, and nanoHub, but Apple does not let people use, which is called tile. If I select tile, CompuCell will redraw the screen so that you can see all of the things that are active at that time. So again, Windows, tile, one of the most powerful things that Player has to offer. This simulation is actually a very interesting simulation of slime molds and their behaviors. We're not going to be exploring it today. We're just using it to get access to CompuCell. To get access to CompuCell, we need to go into this steering panel where it says simulation type. We're going to pull that down and select maze. And you'll see a simulation will start to run, showing slime mold moving in a maze. And for the people who are doing nanoHub, I want everybody to do that and make sure that this works. If anybody's having trouble with that, speak up and we'll help you out.
I'm sorry, I'm lost. I get lost. I am now logged in nanoHub, but I don't know where to find the CC3D tool.
Right. So I'll walk you through that again.
Thank you very much.
Can you find your desktop? If you go and you see the screen that I have here with on my screen. If you come to the top right, you should see menu. Do you see that?
I've loaded a CC3D tool, but it's said vascularized tool or
Okay.
something like this.
Right. So you'll need to run a specific tool.
Okay.
So go to your desktop
Mm-hmm.
dashboard here. Okay. We'll go to dashboard. Let's get that to run. Hope it'll run.
Okay.
Sometimes nanoHub misbehaves, so we'll see. Is nanoHub going to let me go do what I need? Okay, let's see. Where's my dashboard? All right, doesn't want to let me go to my dashboard, so I'll have to wait a second. All right, come back to the main nanoHub. Okay. Okay, takes a minute. Here's dashboard. Okay, can you get to this screen? Okay.
Yeah,
Okay. Go to all tools under my tools.
all tools. Right.
Okay, in this little box that says search tools, type the word SLIME, slime.
Great.
Okay, it will pull up CC3D slime mold simulation.
Okay, I get it.
Click on the heart. That will pin it to your desktop.
Okay.
And now click this button here, the little rectangle, and that should launch it.
Perfect.
And then you should get a screen that looks like this.
Perfect. Now I'm in. Thank you.
Great. Now, once you've gotten in it, to start it running, you will first have to go to Window and select Tile so that you can see everything. And then you'll see something called Steering Panel. In the Steering Panel, I'll make this a little bigger so it's easier to see. You'll see Simulation Type and then some other things. Under Simulation Type, you're going to have to pull down and select Maze. M-A-Z-E, and the simulation will start running.
Okay. Thank you very much.
For you? Did that work for you?
Now it's launching, but I know what to do now, right now. Thank you.
Perfect. Thank you. I know this is a little bit of an inconvenience for today, but once after today, we won't have to do this. All right. All right. If you're running a simulation, you'll see these three buttons at the top. There's a square which stops the simulation and you have to restart from the beginning. There's a run button with a dot here which plays the simulation. There's a pause button that halts it temporarily and allows you to restart. And there's a circle which steps it one time step forward at a time. For the moment, start the simulation running and then hit pause. And now what we're going to do is create a little CompuCell simulation and run it together. Again, the people who are using desktop, all of this is extra. You can jump to this step immediately. We're going to write a simulation using the editor, Twit. And so if you're in desktop, what you're going to do is simply launch Twit. Make sure that that's running. If you're in nanoHub, you have to start Twit. And you can start Twit by pushing this little pen and paper icon here, or you can go to File and select Start Twit. Either one of those will work. So why don't you do that? We're going to go to this little pen and paper icon. We're going to hit pen and paper icon. And a new window will open. And this is an editor window. Is that working for people? Okay, great. You'll notice that there are two tabs. On desktop, editor, player, and Twit are separate applications. And so you'll switch back and forth between them as separate applications. In nanoHub, there are tabs within the same application. So if I click here, I see the simulation run. If I click here, I see the editor. Okay. So now we should be back in sync, whether you're desktop or nanoHub. Again, if you get misdrawing and misdrawing in nanoHub, pull that bottom right-hand corner a little bit and get things to redraw. To launch Twit, we've done that. We've got Twit running now. So everybody should have Twit running. Now we're going to create a new simulation, and I'll walk you through the steps verbally once, and then we'll do it together, okay? So the first thing we're going to do is we're going to say, create a new CC3D project here, like that. That's under CC3D project. We'll pull down that menu, and there's a button called New CC3D Project. And you don't have to do that now. We'll do that together in a second. That's step one. Step two, that will open a window that asks us what we want to call the new project. And we'll give it a name. And it's going to be important that the name not start with a number or a special character and not have any spaces or special characters. And we'll keep hitting this next button to go forward. It will then ask us when we want to do things, we're going to have to say where we're going to put the simulation. And we'll browse and we'll select the location for the simulation. And it's important that the place you put the simulation is the place you have write access. So if you're on a Mac or a Windows machine, you probably want to put it on your desktop. If you're on nanoHub, you'll have to select your username because that's where your local storage is. If you try to create a simulation in a place where you don't have write access, CompuCell will crash. And if Twit keeps crashing on you, it's almost certainly because it's pointing to a place that it can't write. The next thing you're going to do is say how big the simulation is, and we're going to accept the default settings. Then you're going to create two cell types, cell 1 and cell 2. Then you're going to skip the chemical fields. We're not going to create any chemical fields. And then you're going to define the features that the cells have. We're going to say that they stick to each other, they have contact energy, that they grow, that they divide, and that they have a volume. And then we're going to say next, and that will create the simulation. Okay. So let me walk through that with you now, and we'll do that together step by step. So step one, we go to CC3D project and select new CC3D project. And everybody follow along, do this with me. You could call it my first simulation, would be all right. Any name, as long as it doesn't have spaces or special characters and doesn't begin with a number or special character. In my case, I think I've used that name multiple times, so I'm going to call it my simulation 7 or 8. Now, the next thing we have to do is we have to select the simulation directory. So we're going to hit Browse. If you are on a PC or a Windows machine, you would select your desktop. If you're on nanoHub, you select the folder with your name. Here, hit Choose. The next thing we want to do is hit Next. And the way my CompuCell is configured here, the Next button was hidden. And so if you don't see the Next button, you can pull on the bottom right-hand corner of the window to make sure that you can see it. Alternatively, Hayden says that if you hit Alt and then use your mouse on it, it'll work as well. So is everybody be able to see this window and then hit Next? Did that work for people? Does anybody need help? Okay. The next window asks you how big you want the lattice to be, how long you want to run it. We're not going to change the settings, so we'll just hit next. The next thing we're going to do is we have to tell this CompuCell what kinds of cells we're going to have. In this simulation, we'll have two kinds of cells. We could call them A and B, cell 1 and cell 2. No special characters and no spaces. I'll call them cell 1. And I hit add. You'll see it come up in this table here. And I'll type cell 2. I hit add, and you'll see in the table cell 1 and cell 2. Everybody got that? So if you need help, let me know. Does anybody need more time? Okay, we'll go next. It says chemical fields. We're not using chemical fields, so we just hit next. And now this is the key step. We have to tell the cells what properties they have. We're going to say they have contact energy. Click that one. Here, contact. We're going to say that they grow. You'll notice that there are hover over little informational boxes that appear in Twitter, giving you a little information about what it is you're selecting. Mitosis, that is cell division. And we need to hit volume local flex. So contact, growth, mitosis, volume local flex. I'll wait for a second to make sure everybody got that. Give me a thumbs up when you've got that working. Does anybody need help? Don't be shy. If you need help, it's fine. If one of you needs help, probably more people need help too. Okay, is it okay for me to go on? Okay, great. So we hit next. It says configuration complete. I hit finish. And you should see something that looks like this. You'd say, where's my simulation? Nothing happened. You'll see here in the left-hand window, there's the name of the simulation that you typed. If I pull down that or double click on it, it will open and I will create tabs, which are the name of the simulation.xml, the name of the simulation.py, name of the simulation steppables.py. That is the model specification. You can navigate by selecting the tab or by double clicking here in the navigation pane. It's good to know how to save a simulation. Up here, there's the old-fashioned double floppy disk icon. If you click on that, that will save your simulation. When you make a change in your simulation, you always need to remember to click that to save this change. Okay, now we want to run the simulation. To run the simulation, we select the line where we have the name of the simulation. We right click and we select open in player. It'll give us a warning that there's an existing simulation running. We'll say yes. And now, if you're on desktop, the simulation will run. If you're in nanoHub, you have to change tabs at the bottom. And now we'll have to restart that simulation. So I'll hit step. And you'll see the name of the simulation will change. Here at the top, my first simulation, and the display will change. And always remember, window, tile will lay out your simulation. So I'll wait until everybody has this up on the screen. Again, if you need help, ask. And this time, why don't I use the poll to ask you how you're getting along with this? So I'm going to do a poll, which will ask you, how far are you able to get to this step? Sorry, it's the wrong poll. Sorry about that. It's the wrong poll. Here's the poll we need. So I'll wait until everybody has this working. Okay, somebody needs help. Why don't you in the chat explain what you need help with, and we'll do our best to help out. Can I please repeat how to run on the other tab? So you define the simulation here, input it. When you hit the player, it freezes. I'm not sure what you mean by hit the player. You mean that that it doesn't display? Showing the player option. Okay, so here I say open in player. It'll give me a question. Do I want to stop the existing simulation? And then I change tabs and I should see the player. So you're saying that the tab nanoHub is slow on your Mac. I don't know why. Okay. Well, in principle, and I don't know either, because nanoHub, everything is happening executing a remote server. So your Mac isn't doing anything. It's just running the browser. I'm sorry if nanoHub is being slow. Occasionally nanoHub is slow. It depends on how many other people are using it because it's a public server. Okay. In player, if you have player crash, if it really crashes, then what you need to do is hit terminate here at the top. Go back to your desktop in nanoHub and turn on and hit run slime mold again. That'll start it again. Okay, somebody's having trouble with the internet. That one, unfortunately, is a difficulty. If your internet connection is really bad, you may be better off running desktop. Hayden asks, did your player crash completely or did nothing happen when you clicked open in player? Somebody says slime mold froze for me. The slime mold simulation we're not using. We're just using the slime mold simulation to get to the editor today. But you do have to, unfortunately, to get to the editor, you have to start it running. It's not really designed. In other words, the editor isn't really designed to be used from this application. We're doing a workaround for today. Okay, somebody says it's working okay. So how are we doing? Maybe we can see about simulation disappears from me too. Okay. Sharon, maybe you could say what you mean by a simulation disappears.
Well, it disappears and I get a page that says, well, right now I don't have it anymore. It says something about sharing and I have to go back and get back into it. It's almost like what was happening last year when it would quit, but it's a different, feels different, but it takes me out of the simulation.
Are other people having that problem? This is an old version of CompuCell that we're using. So it's possible there is an issue with this move. So maybe I should come back and ask simply, can you give me a show of hands? How many people have this working and how many people have it working? Nobody. One person. Okay. So again, I think it seems to be it's a nanoHub issue. So let's walk through the steps again if it's not working. I'm going to hit terminate. I go back to my desktop. I'm going to restart slime mold simulation. And maybe it'll fail for me now and I'll be able to understand what's happening for you. I tell it okay to the warning. It starts the slime mold simulation. I hit tile. I now start the simulation by selecting maze, and the slime mold simulation starts running. I now hit pause, and I don't need the editor at this point, although I can use the editor. Let me start Twit it. So I'll go to start Twit it, and I see Twit it here is running. I'm going to reopen the simulation I just wrote by clicking up arrow. Open. The simulation is here. And everybody's nanoHub is the same. Doesn't mean it always works, but everybody has the same interface. So what I'm doing here will work on your computer, modulo mistakes in nanoHub. Occasionally nanoHub will get crotchety. Okay, so here I have the simulation. I'm now going to go, if you don't have, I'm now going to go back to slime mold. And probably the easiest thing to do here would be to say, I'm going to stop this simulation. Stop. And now I'm going to go to File. And it says Open Simulation File. People should be able to do that. And now I can find my simulation that I just wrote. I've got a lot of them. You won't, of course. I called it My First Simulation, number 8 here. Open that, select it. And now let's see if it runs. It runs. Again, don't be too discouraged. The reason we're doing this today is so that everybody gets everything working smoothly by the time this course starts. So if we get stuck today, as long as we can get past getting stuck today, you won't have a problem in a month. That's why we have a whole month to get ready for this. Sharon, were you able to get it to work now, or is it still stuck?
I got parts of it to work. I got to twit it. I wasn't sure where the button was before.
Okay,
Hold
so
on.
you're in Twit it.
Yeah, I'm not even going to try to follow anymore. I'm just going to watch because it's hard to go back and forth between Zoom and the browser. It's really hard to follow along. So
Well, this will all be recorded, so you can watch it again if you need it.
Yep, I'm afraid I'm gonna have to do that with every session of the workshop.
Well, we'll do our best, but we can't. Different people have to take it in different ways, and I appreciate your patience. Okay, so let's come back to running the simulation for the moment. If you're here, hit run. Yes, server disconnections usually mean that you're trying to read or write to a directory you don't have write privileges for. So when you created the simulation, if it's on nanoHub, it's critical that you do what I did, which is you browse the location and you select your user directory as the location to write the simulation to. That can happen on a Windows or a Mac machine too, but it's less likely. So now if I hit run, you'll see the cells will grow. I can zoom in by scrolling on my mouse. You'll see the cells grow and divide, and they'll also change type. Okay, we can change the size of the simulation, resize, play. Again, that tool Windows tile is very helpful. If you want to get things set back to 0, hover over the window and hit R, and that will reset the screen. Again, start, circle, step, run, stop, and pause. Don't hit stop unless you really want things to start from the beginning. Let me very quickly talk a little bit about the code. Don't worry about going into the details because we're going to have a whole 2 weeks to worry about that. But I just want to give you a sense of what a CompuCell simulation looks like. There are 2 components to a CompuCell simulation, a CC3D ML file and a Python file. The static properties of the CompuCell are described in the ML file, and the Python describes the dynamics. If we go back to Twit, we should be able to see the simulation. Occasionally, you will get funny line spacing in Twit. If that's the case, go to View and do Zoom Out repeatedly, and that will fix that problem. And I don't quite understand. This is something having to do with the way VTK reads the resolution of your screen. And it's quite annoying when you see it, but it's always fixable by doing zoom out repeatedly. Nobody complained about that particular problem, so I guess it didn't happen to us today, but it has happened in the past. Okay, we're going to look at the simulation, and we're going to first look at the XML. So we'll double click on the XML or select the tab XML here. We'll see that the simulation is in blocks. The first block specifies the size and the duration of the simulation. For example, if we look here, we see dimensions 256 by 256 by 1. That's the size of the lattice that the cells live in. If it were 3D, it would be 256 by 256 by 256. So it's intrinsically a 3D simulation. The second block consists of the list of cell types. We created 2 cell types, cell 1 and cell 2. And there's always a cell type called medium, which specifies what happens where we don't have cells. The third cell block specifies the cell properties. So for example, we said that cells have an adhesion between each other, or contact energy between each other. That has to be specified by every pair of cells. And here we've given them all the same energy. all the cells stick to each other equivalently. And that's normally something we would change in a real simulation. And the last thing that we might want to look at is the configuration. We go to the bottom of the simulation, we'll see something called steppable uniform initializer. And this will draw a square of cells. We specify the bounding box of the square, the size of the cells, and what cell types we want in the box. We could go in, for example, and make that bounding box smaller so that we start out with fewer cells. And that's actually a pretty useful thing to do. But it will warn me that I typed things wrong. So here, if something's red, there's a syntax error. So I've changed the size of the box from 51 to 200 to 51 to 64. When I make a change, I have to hit save. Now let's look at the Python. The Python, again, if this looks unfamiliar, don't worry too much. We'll spend a lot of time worrying about how to make it work. At the top of the Python is a bunch of boilerplate, which we'll neglect for the moment. And then you'll see something that's important. You'll see something called start. This is run at the beginning of the simulation. And then you'll see for cell and self.cell list. This does something to all cells in the simulation. And what we're doing is assigning something called a target volume, the size the cell wants to be, and its compressibility, how much resistance the cell has to being compressed. We want our cells to grow, so we will see something called a step function at each time. We go through our cell list, and we increase the volume, the target volume of the cell by 1. Plus equals in Python is an increment function. And this will cause the cells to grow. 1 is actually pretty fast. I could make them grow more slowly, 0.25. Great, save. The next thing I want to do is that if the cells get to be big enough, I want them to divide. And here I show the Python concept of a list. I create an empty list of cells to divide. I look at all of my cells. If they're bigger than some threshold, 50, we can talk about what that means another time. I say I add that cell to my list. Then I run through that list. And for every cell in that list, I divide the cell. So CompuCell has built in a concept of cell division. When a cell divides, I go from having 1 cell to 2 cells. And so I have to say, what happens to the parent cell and the child cell? What is their relationship? And there's a function called update attributes that takes care of that for you. Here I say that each cell gets half of the original volume, that the child cell is identical to the parent cell, except if the parent cell was of type 1, the child is of type 2. If the parent was of type 2, the child is of type 1. And that's all that happens. So now we can come back, and I'm going to try stopping this, and I'm going to try running it again, and we'll see what happens. And it made a mistake. This is a glitch in this particular version of CompuCell. It's going to come back and try to try to run an older version of simulation. It's going to try to run the slime mold simulation again. And it says some other people had it. Looks like I may have crashed the simulation. As I say, we should have this fixed by the next time we meet. Yeah, it died on me. So you're not the only people who can have problems with this buggy version of CompuCell. I do apologize for it, but that was the fastest way to be able to show you how to edit something today. People using the desktop shouldn't have had this problem. Okay. Preparing for the class and the hackathon, I hope that people are able to get this working. as I say, we're working as fast as we can to get that nanoHub release updated so that the base simulation will work. This annoyance really was just for today. Once you've got working CompuCell locally or on nanoHub, try saving and loading CompuCell simulations. There is a nice set of demos in CompuCell. You could try running a few of those. I particularly like steppable-based mitosis, angiogenesis, and delta notch are nice simulations. You might read a little bit of the material that we discussed. It's not essential, but if you can do it, that would be great. And if you're thinking about participating in the hackathon, maybe think about what project you want to do, what kind of project you might want to join, or if you want guidance from us about what might be reasonable, please come talk to us. So I appreciate your patience with the issue with nanoHub today. And I'm sorry that we've had to do some terminating and relaunching of nanoHub, but we'll have that working for you by the next time we meet. And there'll be a hackathon organizing meeting on July 11th. Is that right? Okay.
Yes.
Okay. Are there
And
any-
the 25th.
Great.
We'll be sending out an email with more details about those next week. So keep an eye on your email inboxes.
And we'll go over, as Hayden says in the comments, we'll go over all of this again at the beginning of the CompuCell workshop. And of course, these videos will be available for you to go through again on your own time to try out things as well. And if the things really continue to not work, either on desktop or nanoHub, please do come back to us and let us know, and we'll do our best to debug. For people who are doing installs on desktop also, we'll do our best to help. Any other questions before we break? I know it's getting late for people. Okay, well, thank you very much for coming this evening. And I appreciate, again, your patience with the issues with nanoHub tonight. And we'll do our best to get everything working for you before the workshop starts.